So we'll get right into it. The previous month of space news. I'll start off with the Vulcan Centaur. That was their first successful launch, or the first launch period. It was successful out of Cape Canaveral on January 8th. Now, this included Astrobotic's Peregrine Mission 1 lunar lander, which wasn't successful. But also there was a small payload that went into solar orbit that went along with the upper stage of the Centaur itself. So some parts of it still survived. A little bit about the Vulcan Centaur, since we haven't heard that much about it lately. First of all, for those who don't know, ULA stands for United Launch Alliance. It goes back to a joint venture between Lockheed Martin and Boeing, created back in 2006. It is up for sale. That hasn't been concluded yet, but everybody's kind of waiting around for that. Blue Origin everybody kind of thinks they'll probably buy them. Cerberus, which is an investment firm, which is interesting, named after a guardian of hell. It's like a three-headed dog or something. And then some still kind of unnamed aerospace company that doesn't have a big space business now. Most people seem to think it's Textron right now. So Vulcan is the name of the first stage, and Centaur is the name of the second stage. They had the Centaur back in the days of the Atlas booster, so that you heard of Atlas Centaur before. Well, now it's going to be a Vulcan Centaur. So development started in 2014, and that's mainly because when the Russians grabbed Crimea, we realized, well, okay, maybe we don't really want to depend on Russia. So ultimately there was some legislation passed about that we had to get off of it because we were using Russian engines in the Atlas V specifically. So they also wanted to create something cheaper than a Delta IV. Delta IV, worked fine, but it was a very, very expensive rocket. So they wanted to basically reduce costs, and they wanted to get rid of the Russian engines. And, of course, a big part starting to happen then was they wanted to be able to compete with the Falcon 9 from SpaceX. That was started in 2010, and around 2015 or so, they started to go reusable, and they wanted to at least be able to compete with that. And in particular because SpaceX had sued, and they wanted to get some government business. And they succeeded at that. And so now, the incumbents, basically the Boeing Lockheed Martin group, they were getting pretty worried because they saw all of a sudden there was a new competitor who probably was going to be a lot cheaper. Some of their goals also were to reuse whatever facilities they could from their old Atlas and Delta rockets. So that included facilities, like hangars and that sort of thing, designs, and even some of the parts. So although this is a new rocket, a lot of the parts on there really go back to designs, if not the actual equipment from some of the earlier stuff. Now, that having been said, they have quite a backlog of orders right now for this thing. It's been delayed. It was supposed to have gone up a couple of years ago. But actually, they have a backlog of orders of 70 for this thing now. 38 of those are from the Amazon Kuiper project, which is their version of Starlink. 20 or so with the U.S. government, then everybody else. A little bit about the design of the thing. It more or less competes with the Falcon 9. It's not quite as high, but it's wider. They did also update the Centaur second stage. The first stage is what's completely different. This now has the Blue Origin BE-4 engines. It has 2 of those. But then they attached solid rocket boosters to them if they want. So if they're doing heavier loads, they put more of these boosters on. I drew an arrow there on the lower right side pointing out those solid rocket boosters. They're not all that big. If you're thinking of what the SLS rocket looked like, you saw these gigantic boosters. You almost don't notice them on there, but it makes a difference quite a bit, actually, in what they can get up into space. So that initial launch had just the 2. They come in pairs. In terms of propellant, because they're the Blue Origin engines, they do use methane and liquid oxygen versus the kerosene, RP1, that's being used by SpaceX. The second stage, though, is hydrogen and liquid oxygen. That makes it more like SLS, or a lot of the traditional earlier rockets were all based on hydrogen. Versus the second stage of the SpaceX entry, they use kerosene. Again, it's called RP1. It's just a refined version of kerosene. They think that does give them an edge because hydrogen is more efficient. It has a higher specific impulse than the fuel that they're using on the Falcon 9. So they think that will give them an edge when you want to go really far. And of course, they have the solid rocket boosters, and that's some combination of aluminum powder and ammonium perchlorate. And there's a polybutadiene. That's what the HTPB is. Anyway, that's what's in those little boosters. So what about reusability, though? Here, everybody was realizing that SpaceX with the Falcon 9 was heading toward reusability, and they didn't really address it. They just kind of ignored that. As a result, they're locked in their design. Stage 1 will always be expendable. There's no choice because they're only using 2 engines. You can't throttle back 2 engines enough so that when you're re-landing a booster like they do with the Falcon 9 or future Starship, When those land, you really don't need much in the way of thrust because most of the weight is fuel, and you've already used up most of your fuel at that point. So they won't be able to do it. But instead, what they've said that maybe what they'll do is they'll try to recover the engine. Up in space, they'll split off the engine. Fundamentally, they're just going to have a really good heat shield. And they've been working with NASA on this inflatable heat shield idea. What's different about that, if you look at this picture over here in the lower left-hand corner, the part in the center is what's basically the size of the fairing, the diameter of the rocket. So it's inflated to be much, much bigger than that. And as a result, you can get a lot more air friction. And what they're hoping to do is just basically use that to absorb all the energy when they come down and then land on the ocean and float on that thing. So they're putting their hopes on that, but they haven't really committed to a timetable for it. Everybody thought that was pretty much like vaporware for a long time, until Amazon came in with all those orders for their Kuiper project, and they've been kind of pushing it to say, well, okay, you ought to do something, because the engine is the biggest piece of the cost for the first stage. And so they figure, well, okay, at least you get that, you get some benefits of reusability. Because without that, they're going to have a hard time competing on cost anyway. In terms of the payload, if you have all 6 of those solid rocket boosters, the SRBs, you get about 60,000 pounds to low Earth orbit. Now, there's specifications on that, on what's the angle that it's launched at and that kind of thing. And that's actually more than the Falcon 9 can do in expendable mode. And if you're doing these kind of comparisons, you have to specify a lot, like how many boosters in the case of the disposable rockets. And in the case of the reusable rockets, then you got to talk about, well, what are you doing with the boosters? Because if you go expendable, meaning you can use up all the fuel on the way up, you can obviously get more up than if you try to recover it, because you need to have some fuel to slow down the booster and bring it back. And then it even matters where you bring it back to. So in the case of the Falcon 9, there's 2 choices. One is to go to a drone ship. That's the ASDS. It stands for something or other drone ship. Because that's way downrange of the direction you've been going, you lose some effectiveness. You go down from 50,000 pounds down to 41,000 pounds of ability to carry payload. If you do a return to the landing site, that takes additional fuel, and so actually it's less, so it would even be a smaller number than I'm showing there. So with all the boosters in place, the Centaur could actually get more stuff up there than a Falcon 9. Now, of course, the Falcon Heavy could still do more than that. So the Falcon Heavy would still win before Starship comes along. Now, on the other hand, the rocket itself, if you don't have any solid rocket boosters, it can only put up about 24,000 pounds. So in that sense, it's actually smaller than the Falcon 9. A similar thing applies if you're going up to geosynchronous orbit. Obviously, it's a lot smaller payload you can get up there. And again, they can get a little bit more than a Falcon 9 can, but not as much as a Falcon Heavy. In terms of launch costs, that's what really matters to the people that are buying these launches. Who knows? Because the contracts that have been out there so far are pretty much government and maybe not really fully announced. And then the Amazon Kuiper stuff, that's all a special price for them. And who knows whether they made money on it or not. People have guessed it'd be between $100 and $200 million for a launch, depending on how many solid rocket boosters, depending on the orbit you're going to, and so on. If you look in the Falcon range, either Falcon 9 or Falcon Heavy, the range there is probably 60 to 120 million right now. And actually, a lot of people think that they could probably go quite a bit cheaper if they had to. They just don't need to, because they're already the cheapest, so it doesn't really matter. But there, as I said, the comparisons do depend on how much reusability you're going for. If you're expending it, it costs more. You got to build a new one. If you're reusing it, it takes you a little bit more fuel, but on the other hand, you reuse the rocket. Overall, reusability has definitely worked out for SpaceX. Okay, moving on to a different topic. A lot of stuff going on with the moon. Let's start with the bad one, Astrobotic. They had the lunar lander called the Peregrine, and it had a failure, which was really too bad, because this was the first U.S. lunar lander since the Apollo program. We're talking 50 years plus there. This was funded in part by NASA, the commercial lunar payload services. They paid for some of the R&D and basically the service, but people had to invest their own money, and they had to go out and get their own customers. Some of those customers, in turn, were governments, including the U.S. or others, as well as some private companies. And there were some private companies that put some payloads there. So anyway, this was launched with that new Vulcan rocket. And as we said, the Vulcan rocket was fine, but the Peregrine lander didn't survive. What they think happened, the fault happened soon after separating from the Vulcan rocket. So there was an apparent leak. What they think might be happening is that they use helium to pressurize the system so that you can control the flow very well going to the engines. And they think that when they were trying to close that valve off to stop the pressurization, it leaked, or at least it didn't close all the way. And as a result, the pressure ended up getting so high that they think they blew a hole in one of the propellant tanks. I think maybe the oxygen, I forget which one it was. That was their theory. They don't actually know that yet. But as a result, one, you have the propellant leak. So, of course, that's going to probably endanger the mission right there. But the other thing is because there's a leak, that's like having an attitude thruster. You got to counteract that. So you then had to use fuel to make up for the fact that there was a leak, just to keep it from spinning out of control. And as a result, they had some trouble keeping the solar cells oriented toward the sun. They managed to get that under control, but they couldn't do much about the leak. And it's slowed down over time, which you expect as the pressure drops, the flow rate is going to go down. But still, not doing it. This shows you the orbit they were taking. They launched from the Earth. They were going into they started the elliptical transfer orbit to get to the moon. And this shows where they were on the 12th of January. They actually got out as far as the moon. But unfortunately, the moon wasn't there yet. Because the moon's up here, up toward the top. It was going to be another 5 days when it was going to get down there. So what they were doing is they were actually going to have another loop around the Earth. That was part of the original trajectory. They weren't going to be able to land anyway. They just said, well, okay, let's just bring it back to Earth, and if we still can control it, we can even control where it landed. And so they did. They think they probably managed to put it down in the middle of the ocean where they hoped to put it. They had enough fuel and enough control left to do that. So then they said, well, okay, let's make the best of a bad situation. At least power up all the payloads and see if they work. Because some of those things were things like measuring radiation. There are a bunch of payloads for instrumentation, and they could try all that stuff out. There were a total of 20 payloads on this thing, 10 of which required power, and they all seemed to work. But still, they didn't do the landing. And on January 18th, they burned up in the atmosphere. They derived that simply by the fact that they lost contact. But also, the U.S. Space Command confirmed that, yeah, it looked like that was probably it. So it's done. It's over. Now, there was the next one, Japan. They landed the SLIM lander, which stands for Smart Lunar Investigating Moon. Yeah, they're not too good on definite articles, so they left out some of that stuff. They landed on the moon. They actually did succeed in landing. This is done by the Japanese Space Agency. This is different than the previous one that did crash, which was a private effort put out by a private Japanese company. They did a successful landing. Now, they were landing in an impact crater nowhere near the South Pole like a lot of the future landers are going. Their big thing was they were going to do a pinpoint landing. And they're saying that's really kind of important if you're going to actually be settling in space and doing things like resupplying missions. You have to be able to land pretty accurately. One reason, just so people don't have to go so far to get the supplies. And the other thing is so you make sure you don't land on really uneven areas and that sort of thing. So they were focusing on landing within 100 meters, which is a whole lot better than anybody has ever done before. Usually the area that you're shooting for, you're aiming within kilometers of that, not meters. And here they're talking about 100 meters. So this was significantly better. They don't know for sure if they really accomplished that. Apparently, they have to wait for some observations from lunar satellites to really pin it down exactly. But they're pretty sure they probably did land very close to where they wanted to. Now, they had 2 rovers associated with this thing. One of them was really a hopper, and it was actually released 6 meters before landing. The hope was it would come off, and then it would actually be able to capture the landing itself with their cameras. And it had its own direct communications to Earth as well, which is interesting. The second was a much smaller one and didn't. But I haven't seen whether they actually got those pictures or not. That remains to be seen. Now, there is a problem, however. They landed successfully. However, their solar cells are not generating electricity. So they've been running on batteries. Now, they said, and this was yesterday or the day before, they said, well, there's only really a few hours left before the batteries run out. So they're not sure what's happening. And the question is, well, what's wrong? Well, one possibility is that there was some kind of a wire break or something. Another possibility is maybe the thing rolled over. There's a picture here. They had very specialized landing. They wanted to be sure they could land on a slope. And you figure if you want to land where you want to land, it doesn't always going to be flat. So they were at least targeting at least handle or 15 or 20% kind of a grade. So what they were going to do is, it's shown in the lower left corner of this picture here, they would come down as they got close to land. They're still moving in the horizontal direction here. They would basically tip over, kind of bang the surface a little bit and land and basically stabilize. Notice that in this picture in particular, the solar cells are all on the top there. So if they didn't quite get this right and the thing just rolled over, well, that would also account for why they're not getting solar power. You'd think they probably could have just had some arms or something stick out to stop that. They apparently didn't. Now, this is like most of the landers that went up there recently, except for the Russian one, which crashed. Most of them, including this one, do not have a radioisotope heating system or electrical power generation. So they won't survive the lunar night anyway, or at least they probably won't. If they do, there's a chance that depending on the orientation of the solar cells, after the next lunar night, maybe something will start back up. So that remains to be seen. But for now, you have to pretty much assume this thing is dead. pinpoint landing, but then you roll over at the end. So, like all of these unmanned probes, you can take a long time to get there. And theirs took months, unlike the previous one, which was not that bad. What they did was when they take off, they actually did a couple of loops around the Earth. We talked about the Oberth effect before, where when you're in orbit, an elliptical orbit, when you're in closest to the Earth, if that's the ideal time to gun the engines if you want to actually increase your altitude. So you did a couple of loops of that. Then they went out and got an assist from the moon, but they didn't try to land there. They were just getting a gravity assist to pull them up into a little higher energy orbit, swinging then all the way around, finally meeting up with the moon. That was their orbit. These orbits are complicated to calculate because it's really not just the Earth and the moon. Actually, by the time you get way, way out, the farthest away from the Earth, the influence of the sun, it has to be in there too. You basically have to have computers to do these calculations well. This is actually an old slide. I used it when we covered this last time. These are the two mini probes, or rovers. The first one was the Hopper. They figured it'll jump about 6 times. This is the one that has direct-to-Earth communication, so still waiting to see, did they manage to transmit a picture? Because that'll tell us if the basic lander rolled over or not. And the other one is a spherical probe built by a toy company. It looks like something out of the science fiction show. It kind of opens up, and then it can roll around slowly. They had one of those on that last private Japanese lander as well. Okay, moving on to something different here, Amazon's Project Kuiper. Now, we covered that in quite a bit of detail last month. This is the Amazon's version of Starlink, which is internet service provided by satellites. But there was one thing. We gave the presentation back on December 9th, and we said, well, it's going to not look as good as Starlink because it doesn't have links between the satellites, which I'll explain in a second. It turned out on December 14th, just 5 days later, they revealed that secretly they have been doing this. They tested it, and they will have these inter-satellite links using lasers. Why does that matter? Now, this is the same slide I used last time, so I'm not going to spend a lot of time on it. The satellites here are shown going kind of across the top of this diagram here. If you don't have links between the satellites, that says if you're a user on the left-hand side, and say you're trying to communicate with something way back here on the right-hand side, you have to go up to a satellite, and you have to bounce back to a ground station. It's called a bent pipe architecture. That's what a lot of the old traditional satellites were like. And from there, if you happen to have an internet connection, then you use land-based internet. If you don't, then you have to go back up and back down. And so we said, well, that's actually kind of inefficient, because if you can just transmit directly from satellite to satellite, first of all, it's a lot shorter distance. It's pretty obvious from that picture. Going down and back up and down and so on is kind of slow. And even compared to land-based internet, it's actually a lot more direct because you can pretty much pick a direct path. If you're going, say, between continents, if you're using an internet connection between your house and Africa somewhere, the path that it has to go through is very, very circuitous. So it's much more efficient if you can just go from satellite to satellite, at least if you're using a laser connection, which has a lot of bandwidth, so you can squeeze a lot of data through it. And that's what they're doing. They're using lasers. So if you have these inter-satellite links, you can just make the system a whole lot faster, much more usable. And that's what they've done. And in particular, then you don't need so many ground stations. You can cover the middle of the ocean because even though there's no ground station anywhere near you, they can transmit among the satellites back to one that does have a ground station nearby. So it turns out they're going to be very, very competitive. Okay, Starlink, a different topic here. On January 2nd, they launched 6 of their newer satellites that are having what's called direct-to-cell technology. And this is the technology where you can take your regular cell phone, unmodified, and communicate via satellite. How do you do that? Well, basically you use really big antennas, and they have to be phased array so they can be very, very focused on a particular area. And they have to have a lot of power for transmit, but they also have to have very, very sensitive receivers so that that little tiny 0.2 of a watt transmitter you've got on your cell phone would reach all the way up there. But it will work. Basically, the satellites act as flying cell phone towers. Just think of it as a cell phone tower, except instead of sitting on the ground somewhere, it's just flying overhead. And maybe it takes, say, 6 or 7 minutes for it to go from horizon to horizon. So you have to have a whole series of them. And we said big antennas. On Starlink, they're adding a 16 by 16 foot antenna. The astronomers aren't going to be too happy about that one. But actually, that's a lot smaller than the competition. There's several other people working on this. AST SpaceMobile, in their small-scale tests, they're using a 26 by 26 foot antenna. Their full operational ones, which are going to start launching this year, they're like 42 by 42 feet. They're huge. You need that if you're going to communicate long distance. Normally, you figure you're going to a cell phone tower from your phone, maybe you're going 30 miles or something at most, and here you're doing 300 miles, so it's quite a bit more. Anyway, all of this, the way they're going to work it is they're not competing with the phone companies. Actually, they're getting buy-in and investment from the phone companies. So using the diagram here, you have a cell phone that's on the lower right-hand corner. You're going to talk to a satellite. That comes back down somewhere to a ground station, Starlink network. Then you go through to the phone company, and then they transmit out by whatever means there is. So that's the model. As a result, they are working not in competition, but actually as partnering. So SpaceX has partnered with T-Mobile and a bunch of other companies. Now, the thing is, you just don't have that much bandwidth available when you get right down to it. So they're really going to start with just text messaging. And that's probably all it's going to be for quite a while. Anyway, they've actually tested this. They just put up these satellites back on January 2nd. The test started on January 8th, and they finished, and they announced them on January 10th. They said it worked fine. They used regular T-Mobile phones, fourth generation LTE kind of phones, normal frequencies, and it works. So the FCC had already authorized large-scale testing, meaning up to 840 satellites. Now, unless they've secretly already put up some satellites that had this capability, I don't know how they're going to get to 840 by June. But anyway, that's what they're doing. There is competition for this. Now, they had to emphasize the market here is just covering dead spots. Even in the U.S., which has very good cell phone coverage, you go out to a lot of national parks, maybe out in the middle of a lake somewhere. There's a lot of spaces where there's just dead spots. Amazon highlighted that when they were talking about their system. They were saying there's places within 50 miles of their headquarters near Seattle where they don't even have cell phone service. So it will fill in. It'll also fill in during emergencies. When cell phone towers go down, your phone will just automatically take the next best option, which is going to be overhead. They're competing against several companies called AST SpaceMobile, another one called Lynk. In a sense, they're also competing against Globalstar, which is what Apple is already using for their emergency messaging. And Iridium, they'll come along later. They were trying to do something similar, but with a proprietary system, and nobody wanted anything to do with that. So that's just not happening. And AST, they're getting a whole bunch of investment from AT&T and Google and Vodafone, they already had investment from. So there's a lot going on with AST. They're going to put up satellites this year. Lynk already has limited service. It's only in some Pacific islands right now, but that's a start. But they're actually offering it commercially in those places. So this is coming. These pictures just show you what some of their systems look like. In particular, that one on the right, the 42 by 40 foot antenna on the lower right-hand corner, that's the one from AST SpaceMobile. Okay, moving on to a separate topic. Artemis, which is the manned space program going to the moon. Everybody knew that it wasn't really going to make the deadlines they had, and they finally made it official. So Artemis 2, which is the next mission, is a lunar flyby, the one where they just go out to the moon and fly around it and come back. That's been moved back from 2024 to September 2025 officially. Artemis 3, which is the crewed landing, that's moved back from 2025 to September of 2026. Of course, they gave reasons for this. There's a lot of them. One of them is the Orion heat shield. They had some disturbing result from the first one. They weren't quite sure how well it's really going to perform. So there's concern about that. They had some problems with batteries too. I'm not sure what those were. Spacesuits, there's worries that they'll really be able to get those in time. And concerns about Starship. It's kind of gotten held up somewhat. They have a lot they have to get done. Well, one, they have to prove that it works. Another one is they have to prove the in-space refueling, the whole human lander system. There's a lot of stuff that has to work in a fairly short period of time. So they just said, okay, let's put it off. Realistically, they're probably not going to make these either, but at least they've officially moved the goalposts now. And miscellany, the Psyche probe. Psyche is that asteroid. That's the one that's a metallic asteroid. They're basically prospecting the metals on that. Totally unrelated to that, they're testing out laser links for deep space use. And that's actually the first time. Now they sent back something from 19 million miles away on a laser link. So that is definitely a record. But they had some fun with it. They sent back a cat video. This is ultra high definition, meaning twice as big in each dimension as normal HD at 267 megabits a second. So it was actually a pretty impressive demonstration that you could essentially do live streaming from 19 million miles away. Okay, now we're at the point where we ask, how many launches do you think we've had since our last meeting? And that's been interesting because the numbers have been going up over time. And the rules are that, one, they have to be trying to get to orbit or beyond. And the other thing is that you count a failure as long as they got off the launch pad. That obviously includes the Vulcan Centaur. It does not include things like Starship, which so far, the first two, they weren't really trying to get to orbit, so those didn't count. Anybody want to take some guesses on how many we've had since December 9th?
16.
Okay.
25.
Oh, you guys are thinking way too low. Now remember, we had more than a month here, so Well, anyway, let's just jump right to it. The answer is 33. So what were some of those things? We have a lot of the usual suspects. You have Chinese military satellites, spy satellites and communications and whatnot, guaranteed. And some of them are interesting ones too. Like, they have their equivalent of the Air Force X-37B, which is like a small scale version of the space shuttle, but it's unmanned and it's a lot shorter. They have their version of that they're on their third flight. The Chinese are testing a recoverable satellite. Now, we've talked about that a little bit among private companies in the US. They want to do, for instance, manufacturing in space. So this says you got to send something up, you make some pharmaceuticals or something, and then you bring it back. Well, the Chinese are experimenting with that also. That was one of their tests. Let's see, now moving down here, Alpha Firefly did a launch, and it's a partial fail. They did, in fact, put something in orbit. The problem was it wasn't the right orbit. And that orbit, it turns out, is only good for about 2 weeks. This happened to them last year. I went back, I was doing yearly summaries of these things, that's what I get to in a minute. And last year I had a footnote in there that, well, we had a partial failure from Firefly because they didn't quite get to the right orbit and it fell out in a couple of weeks. Same thing's happening all over again. Of course, we have tons and tons of Starlink launches. That's the mainstay, really, of what's going up there. I skipped over one here. It was kind of interesting. There's a Russian weather satellite going up called Arctica M. Obviously, it's for the Arctic use. That's going in what's called a Molniya orbit. Now, usually, when we think of satellite orbits, most of the time you're thinking about circles, right? I mean, you think it's a perfect circle. They're not necessarily always. In particular, this kind of orbit, very, very elliptical, highly elliptical, in fact. And also, instead of going around the equator, which is 0 or 90 degrees, which would be polar orbit, it's up there close to that. This is commonly used by Russia, and the US has done a couple of these too, but mostly Russia. And the reason is, when you have an elliptical orbit, the satellite is going fastest when it's closest to Earth. That's the bottom point here. And these are labeled in hours. So say at hour 0, or say you're down here at the bottom of this picture, as you're heading up, you go slower. And so you have a lot of time, in this case, over the Arctic, which of course is what Russia wants because they're mostly in or close to the Arctic. There are some of those satellites up there. There have been. They've been doing it since the 60s. We did some, partially for missile launch detection. You want something that can look at the northern hemisphere really well. There are some other advantages to these orbits. For instance, it takes less energy to get them launched up there compared to, say, a geosynchronous orbit. But those had the additional problem that those are around the equator, which means you're not getting a very good view of the top of the Earth from those anyway. There are some downsides to these orbits. One is you have to pass through the inner of the Van Allen radiation belts. It's about 19,000 miles where it's the worst. So the geosynchronous satellites at 22,000 miles don't really spend much time in there. They get up there and then they're avoiding that for the most part, the worst of it anyway. This thing has to plow through it a couple times a day. So it's a little tougher on the satellites. Anyway, just continuing on page 2, we've already talked before about like the Chinese. They have their GPS equivalent, just like the Russians with their GLONASS system. Everybody wants their own because they want to be able to control it in case it's used for military purposes. There was actually a launch of our space plane, the small pilotless space shuttle. There's a second test satellite for what's called SatNet, which is going to be a huge Starlink kind of equivalent by China. That's coming up. So that's their second test. They're getting pretty close to getting ready to start launching these things. I highlighted a couple of these, one from India and one from China. They don't just only do military things. Actually, sometimes they do pure science missions. India did one here with the Space Observatory. And then down here at the bottom, there's one called the Einstein probe. And this is actually a joint collaboration with the European Space Agency. But it's an astronomy observatory. They're looking for things far away in the universe and probably not much military application there. We talked about the Vulcan launch, of course. The Chinese space station periodically gets resupplied just like the International Space Station does for us. So they've been sending up theirs. Oh, yeah, there were a couple of sea launches, but I ran out of room. I can't remember which one it was now. But the Chinese do a lot of those. Well, one, they have a lot of solid rockets, partially because of the military orientation and history. You normally use solid rockets in military uses. And they're short on launch pads right now. They're frantically building more and more. So they want to be able to launch whenever they want to launch. So they're doing a lot more sea launches. And look at this, Axiom Space, the private crew going to the International Space Station. I say that because our next speaker is from Axiom Space. Okay, but just to wrap up on where are we in terms of launches to orbit. So again, this does not include Starship because they weren't actually trying to get to orbit. They came darn close, but they weren't actually trying for that. So it doesn't include those. Some of the figures you'll see vary a little bit, and that's one place where it varies. Sometimes the other people actually have included Starship in that. So total worldwide launches, there were 200, the way you read this is the total is 221 for this year. Of those, 212 were successful. And of course, there's a definition problem on, well, what is success? The Firefly being the one that always makes things confusing. So if you look at the totals here, we've obviously been going up. So back in, a few years ago, we only had 100 a year, 114, 134. Now we're up to 221. I mean, it's going up rapidly, and it's going to be a lot bigger. By the way, so the U.S. is still ahead in this. We've launched 114. Now, of those, 96 were from SpaceX, mostly Falcon 9, some Falcon Heavy. All these beat all the records in the past, and by all indications, we'll blow that away next year as well. Just Falcon 9 alone is probably going to launch 150 times this year. Okay, so the U.S. has the most launches. China after that at 67. They only had one failure. Russia, way below that. But at least, they are still in there. Europe is kind of fading away. They're in between. They had their old expensive launchers, and they stopped making those. And now they have their new expensive launchers that don't work yet. So they're kind of, in between being behind and being further behind. Actually, India is outclassing them at this point. They've launched 7 times. Now, this is not counting mass. This is just number of launches. In terms of mass, actually, again, the U.S. wins by far, mainly because of Starlink. The sheer number of tons that's been put into orbit is like 10 times what everybody else does or something. It's some huge number. Then there's a smattering of other countries in here. North and South Korea, Japan, Israel, and Iran have all put up some satellites.
When it comes to the purposes that are listed on there, where does that information come from? Because it lists, China, and the purpose was such and such.
Well, China's the toughest one because everything is dual use for them for the most part, because there isn't that much separation even between the private companies and the others. So it's a little hard to say. They have a stated purpose. Usually they'll say like, Earth observation satellite or weather satellite. And that probably is true as far as it goes. But then, like in other examples I gave, well, maybe besides watching the oceans, maybe they're looking for submarines also. So there's, what is it? A spy satellite? Is it just Earth observation covers a lot of ground? And it's kind of true for us, but we have more of a separation. We have ones that are definitely spy satellites, and then ones that mostly aren't. So, but they may be commercially. So, for instance, for satellite reconnaissance, if you were getting pictures of spots on the ground, the U.S. government would just go out and buy them from the commercial providers. And they like that because, say, in the example of when Russia was getting ready to invade Ukraine, they could just go out and buy those and they could show them to everybody. They didn't have to reveal what their capabilities were. They just used the commercial ones. So, is it a spy satellite? Is it a Earth observation? It's kind of hard to say. Okay, well, I think we're ready. So, Megan, I guess you're up. Other space-related videos or slide presentations by me are available at the link shown here. That includes a web page and also a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and the link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.